Hello, in this video we're going to talk about work, and we're going to write down the work kinetic energy theorem. So let's start with a simple statement that's going to drive this whole discussion here, which is how does force fit into all of this? So a force, not a work, a force, this is me trying to type and talk again, that never works. So let me say and then type. A work can change velocity, and a changed velocity means a changed kinetic energy. There, much better. Because kinetic energy, like we saw in the last video, is 1/2 mv squared. So let's write that down as a reminder since we just went over it. And so changing velocity changes the kinetic energy. We're also going to look at why is there a 1/2 in our definition. It might not seem so weird to take mass and velocity and mix them up in some way that's a useful number for a system, but why a 1/2? And that is a seemingly arbitrary thing. We'll look at where that comes from in just a little bit. So let's look at how a force changes the velocity of a system. So force is equal to mass times acceleration, and when we say force, what we really mean is net force, because we can only have one acceleration for a system. And let's just look at one component. So we'll do this in one dimension. So let's look at the x component. Okay? So that means that the x component of force is equal to mass times the x component of velocity. Great. And now let's write that in terms of a velocity change. So to do that, we're going to use kinematics to replace acceleration with the other kinematic variables. And the equation we're going to use is the v squared is equal to v initial squared plus 2ax, where we are using the x components here. And we'll say delta x, a change in x. Okay, now there were other kinematics equations we could have used. Why did we use this one? We use this one because it's time independent. Time doesn't show up in it. And so this is just simply true for the system. We don't have to worry about how it changes with time. So we can solve for acceleration, and then we'll plug that back into our equation up here. So if we want to solve this for acceleration, we'll subtract v initial x from both sides, and then we'll divide to get to the acceleration's x component. So it's equal to this difference in velocity squared divided by 2 times delta x. Okay, and we're running a little bit short on space. Let's just put this on the next slide. Okay, so we'll plug that into the equation we had on the previous slide, F equals ma, and we're going to get that F is equal to m times that new a, which was vx squared minus v initial x squared divided by 2 delta x. Okay. And let's multiply both sides by delta x, so that on the left we have f times delta x, and on the right we have 1/2 times m times the quantity vx squared minus v initial x squared. And now we have something that kind of looks like kinetic energy. Actually, it looks a lot like kinetic energy. If we break it up into two pieces, we have what looks like, say, a final kinetic energy minus what looks like an initial kinetic energy. Now I say looks like because this is just one component. When we wrote down kinetic energy, like we have here on the previous slide, this isn't in components, this is in terms of a speed. So it's the magnitude of the velocity. That's different than just the x component of the velocity. So this is not quite kinetic energy, but we're really close. So how do we make it kinetic energy? Well, we need the other components. And so we don't really have to redo all the steps. We know what they're going to look like. So for those other components, we just replace the x's with y's and z's. So we're going to have fy times delta y would need to be equal to 1/2 times m times vy squared minus 1/2 times m times v initial y squared. And then we could do the same thing for z. So we're just writing down components in each of these cases. Okay. Now the trick that's going to let us put this all together is that v squared would be equal to its x component squared plus its y component squared plus its z component squared. That's the Pythagorean theorem. That's turning components into a magnitude, and you do that by squaring them all, and that gives you the square of the magnitude. Just so happens we have squares in all of our equations, so it's pretty easy to work with. And for the very same reasons, we can say the same thing about the initial speed. That would be equal to the x component of the initial speed squared plus the y component squared plus the z component squared. So we can use that to add the three equations together, or that's motivating why we would add the three equations together. And what we would get on the left-hand side is fx delta x plus fy delta y plus fz delta z. So we're just adding each of these left-hand sides all together, and that's equal to all the right-hand sides added together. All right. So we're going to have 1 half m vx squared plus vy squared plus vz squared. Hey, that's just v squared. So let's simplify that. It's equal to 1 half mv squared minus 1 half m v initial squared. So again, we're using this trick right here to squish all three of these sides together into just the speed. So now it really is the kinetic energy. On the left-hand side, we could write this as a dot product. So this would be like taking the vector f with its x, y, and z components and dotting it with some other vector that had delta x, delta y, and delta z as its components. Let's just call that vector d, okay, where we're just going to define vector d as delta x I hat plus delta y j hat plus delta z k hat. So it's some tiny little vector that points in some direction. That's why we use d here, d for direction. And on the right-hand side, we have one kinetic energy minus another. The final minus the initial, so that's the change in kinetic energy. Okay, so let's try and gather our thoughts on the next slide. In short, we could say that there is three main observations here. The first observation is that we had this f dot d. We're going to define that as work. This is a definition. So work is by definition the force dotted with some displacement. And if you think back to a few chapters ago, what is a dot product? Well, dot product is the magnitude of one vector times the magnitude of the second vector times the cosine of the angle in between these two vectors. Okay, and like I said, we're going to define that as work. So I say that this is the work done by force F. So force F does work. Now we made the assumption here that F is constant. We'll look at in a little bit what happens when force isn't constant. We'll do that in another video. But we didn't say anything about F changing as a function of time or position, because that really should be showing up here when we're doing kinematics, unless it's constant. So another observation, now that we've defined what work is, at least as an equation what work is, what does it actually mean? So work is the change in kinetic energy. That's this result here near the bottom of the slide. The work is the change in kinetic energy. Work is what changes kinetic energy. So when a force pushes on something or pulls on something and makes its velocity change over some distance, that is work, and that is also the change in kinetic energy. And we call that statement the work kinetic energy theorem. Okay, and then our final statement is simply that the unit of work is joules. Since the unit of kinetic energy is joules, the unit of work has to be the same thing, it has to be joules. That doesn't mean that work is energy, but work and energy have the same units. Work is how you put energy into a system or take energy out of a system, as it turns out. So if you think of, an object is just sitting still until a force acts on it and makes it move. If it's moving, then it has kinetic energy. So the force is what, through a work, is what put the energy there. Another statement, just looking at this work kinetic energy theorem, it's possible for a system to have less kinetic energy than it started with. So work can be negative. You might say, well, what's the big deal there? Can't everything be negative? No, not everything can be negative. For example, kinetic energy, which is equal to 1/2 mv squared. Kinetic energy, here's an equation to look at. Kinetic energy can't be a negative number. The only way kinetic energy could be a negative number is if something somehow had negative mass, which is not a physical thing. So nothing has negative mass, at least that we know of. It'd act really weird if it did. And so basically we say that kinetic energy can't be negative. That doesn't mean that all energy can't be negative. Some energies can be negative, but just for a counterexample. Okay, now what if there's a bunch of forces acting at the same time and you want to deal with them separately? Well, that's not so bad. So what we could say, and it's really just a matter of semantics, is that the net work is equal to the change in kinetic energy. We're just being more precise with what we had here. Where what we mean by net work would be the work done by each force were it to act all by itself. But that's no different than just saying it's the net force dotted with the net displacement, which is the same as the displacement. So, just a matter of semantics. You don't really have to worry about if there's one force or multiple forces. You don't have to worry about whether you calculate the net force and use that to calculate the net work, or whether you calculate a work for each individual force. If it were to act by itself and then add them together, you would get the same result. Alright, see you in the next video.